The oceanography bootcamp took place between the two almost identical Maltese bays of Il Ofra Zaira and Il Ofra Bare. Despite the two sharing similar bathymetry and marine biodiversity, Il Ofra Zaira is being used as a water discharge point by the Delimara power station. This sets it apart from its larger sister bay by causing different water temperature, salinity levels, and circulation patterns, while also presenting different health conditions of Posidonia oceanica meadows. Because of this reason, persistent monitoring in both bays is needed to better understand these changes, as well as mitigating possible future damage to the ecosystem. In situ measurements and sample collection took place in 5 different stations, 4 of which are located in Il Ofra Zaira and 1 control site in Il Ofra Bare, as it remains unaffected by warm water discharge.
Il Ofra Zaira is significantly influenced by the Delimara thermal effluent. This warm water discharge alters the local water circulation by creating distinct thermal layers with warmer, less dense water rising and spreading across the surface, affecting both vertical and horizontal mixing. The interaction of the thermal effluent with prevailing winds and tidal forces leads to complex flow patterns impacting the distribution of heat and nutrients. Consequently, the elevated temperatures and modified circulation influence the local marine ecosystem, affecting species distribution, behavior, and overall ecological health.
Thermal effluent, the discharge of heated water from industrial processes such as that of the Delimara power station, significantly impacts marine environments like Il Ofra Zaira. Elevated temperatures cause thermal stress in marine life, affecting their growth, reproduction, and habitat suitability for species such as Posidonia oceanica. Furthermore, warmer water also reduces oxygen levels, leading to hypoxia, which harms fish and invertebrates. Species may migrate or face competition from invasive species, disrupting local biodiversity. Temperature changes impact reproductive cycles and can cause developmental issues in marine organisms.
The instruments that were used to collect the physical data used in this study included a temperature logger attached to the vessel, 4 drifters, and a CTD. The loggers recorded water temperature changes at a constant depth between the 5 study sites. The drifters provided velocity data that could be used to understand the circulation of water within the region. Finally, the CTD was used to observe the change in temperature and conductivity with depth at each site. Such physical parameters can help researchers to better understand the marine environment and the related stressors that may affect productivity.
Posidonia oceanica, or Neptune seagrass, is endemic to the Mediterranean Sea, forming extensive underwater meadows vital for marine ecosystems and organisms. P. oceanica has ribbon-like leaves up to 1.5 meters long that stabilize seabeds with its rhizomes and thrives in clear shallow waters up to 40 meters deep and prefers sandy or muddy substrates. P. oceanica supports marine life, offering food, habitat and protection, while also storing carbon dioxide and producing oxygen. For this reason, it was chosen as the biota for this bootcamp, and samples were collected with the help of scuba diving on each site. To assess meadow health, shoe density and other parameters are analyzed. The control site, in the sheltered bay, shows high productivity with high epiphyte load, suggesting nutrient-rich waters. Site 4 indicates stress with high necrotic length. Site 2 appears healthy with high density and low necrosis. Site 1, which is the one closest to the warm water outlet, shows moderate health with low epiphyte load, and Site 3 has the lowest density and leaf area index, indicating less favorable conditions. These variations highlight the different health and environmental conditions of the meadow in the bay and show that the control site is healthier.